Your home Wi-Fi, a corporate campus, and a cloud data center all move IP packets, but they should not use the same network design. A home prioritizes simplicity and cost. A campus needs scalability and redundancy. A data center needs predictable, high-speed communication between thousands of servers. In the next 10 minutes, you will learn the major LAN architectures you need to recognize for the CCNA exam. A topology describes how devices are arranged and connected. 3 patterns appear repeatedly in real networks: star, full mesh, and partial mesh. Most production networks are hybrids. They combine these patterns depending on where simplicity, redundancy, or scalability is most important. In a star topology, every endpoint connects to one central device. A common example is a group of computers, phones, and access points connected to one Ethernet switch. It is simple to build, expand, and troubleshoot. If one endpoint cable fails, the other devices continue operating. However, the central switch can become a single point of failure unless redundancy is added. Star topology is also called hub and spoke, especially in WAN discussions. In a full mesh, every device directly connects to every other device. This provides multiple paths and excellent reliability, but the number of connections grows quickly. 6 devices require 15 links. A partial mesh provides direct connections only between selected devices. It reduces cost and complexity while keeping redundancy in important areas. Enterprise networks frequently use partial mesh because full mesh becomes difficult to scale. Cisco campus LANs use a hierarchical design with up to 3 layers. The access layer connects users and devices. The distribution layer aggregates access switches and performs routing and policy functions. The core layer provides a fast, reliable backbone between distribution blocks. Not every network needs all 3 layers. The appropriate design depends on the size and requirements of the site. The access layer is where end devices enter the network. It connects computers, phones, wireless access points, cameras, printers, and security systems. Because users and untrusted devices connect here, access switches commonly implement port security, DHCP snooping, and dynamic ARP inspection. Quality of service marking may also begin here. Access switches often provide power over Ethernet, allowing one cable to carry both network data and electrical power. The distribution layer aggregates connections from multiple access switches. It commonly connects the campus toward the WAN, internet, or other network services. Distribution switches are usually multi-layer switches that support both Layer 2 switching and Layer 3 routing. The distribution layer often forms the boundary between Layer 2 and Layer 3. Access-facing links may be trunks, while connections toward the rest of the network use routed Layer 3 links. A 2-tier campus LAN contains the access and distribution layers. It is also called a collapsed core design because the core and distribution functions are combined. This architecture works well for small and medium-sized campuses. The distribution switches provide routing, default gateway redundancy, and connectivity outside the local network. Protocols, such as HSRP, can provide a redundant default gateway, while OSPF can exchange routing information. As a campus grows, directly connecting every distribution block becomes expensive and complicated. Cisco recommends considering a core layer when the network has 3 or more distribution blocks. Instead of forming a large mesh between distribution switches, each block connects to the core. This reduces the number of required links and creates a simpler, more scalable architecture. A 3-tier design adds a dedicated core layer. The core aggregates distribution blocks and rapidly transports traffic across the campus. The core should prioritize speed and reliability. CPU-intensive security functions and initial QoS marking should normally remain outside the core. Connections between the core and distribution layers should use Layer 3 routing. This prevents spanning tree protocol from disabling links that could otherwise carry traffic. Traditional data centers used a 3-tier design, similar to campus networks. But virtualization and distributed applications greatly increased east-west traffic. East-west traffic travels between servers inside the data center. North-south traffic enters or leaves through the WAN or Internet. In a traditional design, communication between 2 servers might pass through several network layers. This can create bottlenecks and inconsistent latency. Modern data centers commonly use spine leaf architecture. Servers connect to leaf switches. Every leaf switch connects to every spine switch. Leaf switches do not connect directly to other leaf switches, and spine switches do not connect directly to other spine switches. Traffic between servers normally follows a consistent path. Source server, leaf switch, spine switch, another leaf switch, and destination server. Because every leaf is the same number of hops away, latency is more predictable. Spine leaf architecture provides high bandwidth and predictable latency for east-west traffic. It is also simple to scale. When additional server capacity is needed, more leaf switches can be added. Each new leaf connects to every existing spine. A leaf that provides connectivity to the WAN, Internet, or another external network may be called a border leaf. At the smallest scale is the small office or home office network, usually supporting approximately 1 to 10 users. A single wireless router often combines several functions: routing between the LAN and Internet, Ethernet switching, firewall protection, and wireless access. Some devices also include a modem. Unlike enterprise networks, most SOHO networks have only one router and one Internet connection. This creates a single point of failure, but lower cost is usually more important than complete redundancy. Here is the final review. A star topology connects devices through one central point. A full mesh maximizes redundant paths but becomes expensive as it grows. Campus networks use access, distribution, and core layers to create a scalable hierarchy. 2-tier networks combine distribution and core functions. Larger environments add a dedicated core. Modern data centers use spine leaf architecture for predictable server-to-server performance, and SOHO networks combine many functions into one affordable device. Once you understand what each architecture is designed to optimize, the diagrams become much easier to recognize and much easier to remember for the CCNA exam.